Hey everyone, this is Bhargav Suthar, and today we will learn what is a Boolean algebra. Now we already discussed what is a Boolean algebra and we did some of the examples. So in this today's session we will discuss some more examples. Fine. So let us recall what is a Boolean algebra. So a lattice. So a lattice A less than or equals to is known as a Boolean algebra or a Boolean lattice if it is both complementary lattice and a distributive lattice. Now we know what is a complementary lattice and a distributive lattice. So in case you don't know, just go for the previous videos. Fine. Now note. Now this we will use. Okay, it is important note. So lattice contains just 2 raised to n elements for any integer n greater than or equals to 0. Fine. And the second note is lattice contains a greatest element and a least element. So this will be very helpful. Now let us discuss example. So the question is, determine whether the following Hayes diagram represent Boolean algebra. So we have total 3 examples. Fine. So we have total 3 Hayes diagrams. So first let's proceed for the first one. So we will create first the LUB and GLB table. See, in previous session only a set and a relation was given. So in that example we wrote the relation, found the Hayes diagram, and then we created the GLB and LUB table. So here no need to do that. So first we will check whether it is a lattice, and then we will go for the complemented and the distributive lattice one. So this is the Hayes diagram. So let us create a LUB table. So the table will be like this. How many points are there? Total 4 points. So 1, 2, 3 and 4, and in row 1. Now least upper bound. So what will be the least upper bound of 1 and 1? As it is the same point, so it will be 1. Now 1 and 2. So 1 and 2 and the least upper bound. So it will be 2. Now as you can see that this 1, it is the lowest point or the least element of the whole graph. So in this row all will be except 1. So that means 3, then 4. Now for 2, now 2, 1. Now in 1, 2 it was 2, so it will be 2. Now 2 and 2. So as it is the same point, so it will be 2. Now 2 and 3. Now 2, 3. So that means it will be 3. And 2, 4. So 2, 4. The least upper bound, it will be 4. Now then 3. Now 3 and 1. In 1 and 3 it was 3, so it will be 3. Now 3, 2. In 2, 3 it was 3, so it will be 3. Now 3, 3. As it is the same point, so it will be 3. And 3, 4. This 3 and 4, the upper bound, so it will be 4. Fine. Then 4. Now least upper bound. Now see, you can see that this 4 is the greatest element. Okay, so greatest element of the whole graph. So what will be the answer? So it will be 4, 4 everywhere. Fine. So this is how you can create LUB table. Now let us create GLB table. So again the table, the symbol. Now 1, 2, 3 and 4. Fine. Now in row also 1. Now 1 and 1. So as it is the same point, so the GLB will be 1. Now 1 and 2. This 1 and 2. So greatest lower bound. So it will be 1. Now you can see that this 1, it is the least point. Okay. It is the lowest point of the whole graph. So this whole row will be 1. Because we are finding the greatest lower bound, and this is the greatest element, the lowest one. Okay. Now 2. Now 2, 1. In 1, 2 it was 1, so it will be 1. Now 2, 2. So 2 and 2, as it is the same point, so it will be 2. Now 2 and 3. This 2 and 3. So greatest lower bound, so it will be 2. And 2 and 4, so again it will be 2. Then 3. Now 3, 1. This 3 and 1, so it will be 1. Now 3, 2. Now 3, 2. In 2, 3 it was 2, so it will be 2. 3, 3. It is the same point, so 3. And 3, 4. So it will be 3. Then next 4. Now 4 and 1. So in 1, 4 it was 1, so it will be 1. Now in 1, now 4, 2. So in 2, 4 it was 2. Now then 4, 3. In 3, 4 it was 3. And 4, 4, as it is the same point, so it will be 4. Fine. So this is how you can find GLB table. Now see. Here you can see that this every pair or subset has a GLB and LUB. So what we can conclude, we can say that it is a lattice. Now the job of lattice is done. So all we need to check whether it is a complementary lattice or a distributive lattice. So let us proceed for that. So now A has a least element, and now it is a line that is 1, 2, 3, 4. So least element is 1. So in same manner, the greatest element, that is very easy. So it is 4. Now just by that property, number of elements in A are 4. So this 4 can be represented as 2 raised to some integer part. So that is 2 raised to 2. so that property holds. Fine. Now here you can see that every element does not have a complement. How? Just consider this. See, 2 and 1. So this 2 or 1. So that means the least upper bound of 2 and 1. So what is least upper bound of 2 and 1? So that is this 2. And in same manner, greatest lower bound of 2 and 1. So that is 1. Now, so what does that mean? And now in same manner, this 2, 3. So that means 2 and 3. So least upper bound of 2 and 3. So that is 3. And greatest lower bound of 2 and 3. That is 2. Now same manner, just consider 2, 4. Now least upper bound of 2, 4. That is 4. And greatest lower bound of 2 or 4. That is 2. And so that means A is not a complementary lattice. Why? Because see, here we need to have this 1 or 4. That means the greatest element or the least element. So, but here it is 1, but here it has to be 4. Now here it is nothing. Here we don't have the greatest element and don't have the least element. And here also we don't have greatest element and the least element. So what does that mean? It is not a complementary lattice. Fine. So hence this this lattice is not a Boolean algebra. It is a lattice but not Boolean algebra. Why? Because it is not a complementary lattice. So that means no need to go for this distributive lattice. So it is not a Boolean algebra. Now second Hayes diagram. See, before proceeding for all these steps, lattice and complementary and distributive stuff, so we will first use that property. So if that property holds, then we will proceed further. So here the number of elements in this above Hayes diagram are how many? So you can see that this 3, 3, 3, 9 and this is 10. So that means the number of elements in the Hayes diagram is 10. But every Boolean algebra, we know this property. This every Boolean algebra is isomorphic to Boolean algebra having 2 raised to n elements for some n belongs to natural number. Now but here you can see that this 10 cannot be represented as 2 raised to n or 2 raised to some natural number. So what does that mean? So hence it is not a Boolean algebra. Very simple. Fine. So it is not a Boolean algebra. And the last one, last Hayes diagram. Again we will check whether it is a Boolean algebra or not just by that property. So how many elements are there? So 1, 2, 3, 4, 5, 6, 7, 8. So here 8 elements are there. So 8 can be represented as 2 raised to 3. So that means we can proceed further. Now this one is also different. So you can see that there is no GLB for the pairs this. So just consider this AC pair. Now A and C. So what is the greatest lower bound? So A and C. So we don't have the lower bound, greatest lower bound of the pair A and C. Now in same manner, this B and C, we don't have the greatest lower bound. Then C and D, we don't have greatest lower bound, and C and F, we don't have greatest lower bound. You can check it. Okay, so there is no GLB for the pairs. So why we are doing this? Because first it has to be a lattice. Fine. So for lattice, each and every pair has to have this GLB and LUB. So if you find any pair in which GLB or LUB is not there, then we are done, or then we are through. Okay, directly. So here we have 4 pairs that does not have GLB. So what does that mean? So this Hayes diagram does not represent a lattice. So as it is not a lattice, so there is no chance of becoming a Boolean algebra. So we can say that it is not a Boolean algebra. So all these 3 examples are very different. Fine. So this is how you can find a Boolean algebra. Thank you.